Good afternoon, all. In the previous lecture, we discussed the Bessel's inequality. Okay, so today we will discuss some theorems on adjoint operator. Okay, and on linear function and adjoint operator. Okay, let us see the theorem. For any linear operator T on finite dimensional inner product space V, there exists a unique linear operator T star on V such that inner product of T of alpha with beta is equal to inner product of alpha and T star of beta, where all alpha and beta belongs to V. Okay, for any linear operator T on a finite dimensional vector space V, there exists a unique linear operator T star on V such that T of alpha, inner product of T of alpha and beta is equal to inner product of alpha with T star of beta. For all alpha and beta belongs to V. Okay, let us see the proof. Let T be a linear operator on finite dimensional vector space. Finite dimensional inner product space. Okay, on V. Let beta be any vector in V. Okay, so let beta be any vector in V. Let us define a mapping f from V to f by. We have to define one more function from V to f. Okay, by f of alpha is equal to inner product of T of alpha with beta for all alpha belongs to V. This alpha comes from V. Give it as equation number 1. Okay, so we have to prove that this defined function f is a linear functional. Okay, let to alpha 1 and alpha 2 belongs to V be any vectors in V and C be the any scalar. Okay, we have to prove this f is a linear functional. Okay, for this we have to prove that alpha 1 and alpha 2 belongs to V and be any vectors and C be the any scalar. Then by the definition of f, the function defined function, we have f of alpha 1 is equal to inner product of T of alpha 1 with beta and f of alpha 2 is equal to inner product of T of alpha 2 with beta. Okay, from equation number 1 by the definition of f. Okay, to prove that this f is the linear functional, what we have to consider? F of C alpha 1 plus alpha 2. By the definition of f, this can be written as inner product of T C alpha 1 plus T of C alpha 1 plus alpha 2 with beta. Okay, so if T is the linear function, okay, we assumed that T is the linear function, linear operator. Okay, hence by linearity property of T, we have which is equal to inner product of T C into T of alpha 1 plus T of alpha 2 with beta. Okay, inner product of C T of alpha 1 plus T of alpha 2 with beta, since T is linear operator. Okay, which is equal to, by linearity property of inner product space, we have C into inner product of T of alpha 1 with beta. Okay, plus T of alpha 2, inner product of T of alpha 2 with beta by linearity property of inner product space. Hence, we have f of C alpha 1 plus alpha 2 equal to C into f of alpha 1 plus f of alpha 2. Hence, f is linear functional. Okay, hence f is linear functional. Here we showed that f is linear functional. Now, then by the previous theorem, there exists a unique vector beta dash in V such that f of alpha is equal to inner product of f alpha with beta dash for all alpha belongs to V. Okay, give it as equation number 2. How we can write like this? Because by previous theorem, in the previous theorem, we seen that theorem. There exists a vector beta dash in V for every linear functional. F of alpha is equal to inner product of alpha with beta dash. Okay, for all alpha belongs to V. Give it as equation number 2. Hence, from 1 and 2, T of alpha 1, inner product of T of alpha 1 and beta, sorry, inner product of T of alpha and beta is equal to inner product of alpha and beta dash for all alpha belongs to V. Give it as equation number 3. How we can write like this from 1 and 2? Look at here. Here the statement number 2. Putting the value of f of alpha 1 in equation 1. Okay. Hence we get inner product of T of alpha 1 with beta is equal to inner product of alpha beta dash for all alpha belongs to V. Give it as equation number 3. This shows that T is the linear operator on V. Then if T is the linear operator on V, then corresponding to every vector beta in V, there is uniquely determined the vector beta dash in V such that T inner product of T of alpha with beta is equal to alpha beta dash for all alpha belongs to V. Okay, this equation number 3 shows that T is the linear operator on V, then corresponding to every vector B in V, corresponding every vector beta in V, there is uniquely determined vector beta dash in V. Okay, such that inner product of T of alpha with beta is equal to inner product of alpha beta dash for all alpha belongs to V. Okay, now we define a mapping T star from V to V by T star B beta, T star of beta is equal to beta dash for all beta belongs to V. Okay, we define a one function more T star from V to V. Okay, such that T star of beta is equal to beta dash. Hence, equation 3 becomes inner product of T of alpha with beta is equal to inner product of T and T star of beta. Right? The value of beta star here. Okay, from give it as equation number 4 for all alpha beta belongs to V. Okay. Now we claim that this T star is the linear operator. We have to prove that this T star is linear operator. Okay. Let beta 1 for linearity. We have to prove let beta 1 and beta 2 belongs to V be any two vectors and C be any scalar. Then we have beta 1 and beta dash belongs to V, it implies there exists unique vector beta 1 dash, beta and beta 2, 2 dash such that T star of beta 1 is equal to beta 1 dash and T star of beta 2 is equal to beta 2 dash by the definition of T star. Okay. Now, for any vector alpha belongs to V, consider inner product of alpha and T star of C beta 1 plus beta 2 is equal to inner product of T alpha 1 and C beta 1 plus beta 2 by, okay, from equation number 4. This can write, we can write from equation number 4 here, okay, by the definition of this. Okay, we have to prove that the T star is linear operator. Okay, hence which is equal to by linearity property of inner product space, this C comes as a C bar outside the inner product and T of alpha plus beta plus T of alpha inner product of T of alpha with beta 2. Okay, this is beta 1 and this is beta 2, which is nothing but C bar and into inner product of alpha T star of beta 1 plus alpha and inner product of alpha and T star of beta 2 from equation number 2. What is the value of T of alpha? Is alpha the value of this one. Inner product of T of alpha and beta is equal nothing but inner product of alpha and T star of beta 1. And value of T of alpha and beta 2, inner product of T of alpha and beta 2 is nothing but alpha, inner product of alpha and T star of beta 2. Hence, we have inner product of alpha and C of T star of beta 1 plus inner product of alpha 1 T star of beta 2. Okay. Hence, we can write like this. Inner product of alpha T star of C beta 1 plus beta 2 is nothing but inner product of alpha C T star of beta 1 plus T star of beta 2. Hence, we solving this all the step, taking this set, this as this term to the left side, we get inner product of alpha T star of C beta 1 plus beta 2 minus inner product of alpha C T star of beta 1 plus T star of beta 2, which is equal to 0. Hence, by linearity property of inner product space, alpha, inner product of alpha and T star of C beta 1 plus beta 2 minus C T star of beta 1 plus T star of beta 2 is equal to 0 for all alpha belongs to V. Hence, this right side of the inner product is must be 0. Why? Because this is the scalar quantity. For all alpha belongs to V, this term must be 0, which implies that T star of C beta 1 plus beta 2 minus C T star of beta 1 plus T star of beta 2 is equal to 0. Taking this term to the right side, we get T star of C beta 1 plus beta 2, which is equal to C into T star of beta 1 plus T star of beta 2. Okay. Thus, the T star is a linear operator on V. We proved that the T star is the linear operator on V. Okay. Now, to prove that this is the unique linear operator. Okay. For the uniqueness of T star, let us assume that G be any other linear operator on V such that inner product of T of alpha and beta is equal to inner product of alpha and G star of B for all alpha beta belongs to V. We have to prove that uniqueness of T. For this, we assumed that G is the any other linear operator on V. Okay, defined by like this. Inner product of T of alpha and beta is equal to inner product of alpha G star of beta. Give it as equation number 5. Hence, from 4 and 5, we have inner product of alpha and T star of beta is equal to inner product of alpha G star of beta. For all alpha beta belongs to V. Taking this term to the left side, we have inner product of alpha T star of beta minus inner product of alpha G star of beta is equal to 0 for all alpha beta belongs to V, which is implies that inner product of alpha and T star of beta minus G star of beta is equal to 0 by linearity property of inner product space. Okay. Hence, which implies that T star of beta minus G star of beta is equal to 0. Why? Because inner product of two terms is equal to 0 for all alpha belongs to V, then this term T star of beta minus G star of beta is equal to 0 for all beta belongs to V. Hence, we have T star of beta is equal to G star of beta for all beta belongs to V, which implies that T star is equal to G star on V. This proves that uniqueness of T star. Okay. So therefore, for each linear operator on V, there exists a unique linear operator T star on V such that T of alpha and beta inner product of T of alpha and beta is equal to inner product of alpha and T star of beta. Okay. This is the proof of the theorem. Now, the next theorem. Let V be finite dimensional inner product space and beta, the curly beta, is the basis, is the orthogonal basis such that alpha 1, alpha 2 up to alpha 1n be the orthonormal basis for V. Let T be a linear operator on V and let A be the matrix of T in the ordered basis beta That is, A is equal to matrix of T with respect to basis beta. That is, A is equal to AKJ. These are the elements from the matrix capital A. Then that elements, then all these elements AKJ of the form inner product of T of alpha j and alpha k. All the elements in the matrix with respect to basis beta is, is of the form is equal to AKJ is equal to inner product of T of alpha j and alpha k. Okay, let us see the proof of this theorem. Let V be the finite dimensional inner product space and let beta is equal to curly beta. Okay, alpha 1, alpha 2 up to alpha m be the orthonormal basis for V. Okay, this is the orthonormal basis for V. Then any vector beta belongs to V can be uniquely expressed as beta is equal to any vector beta belongs to V by the Bessel's. Okay, for any vector beta belongs to V by previous theorems. Okay, can be uniquely expressed as beta is equal to summation k is equal to 1 to n inner product of beta with alpha k into alpha k. Okay, give it as equation number 1. Let T be a linear operator on V and let capital A is the matrix of T with respect to beta. That is, A is equal to curly bracket in AKJ. Okay, with respect this is the matrix of T with respect to beta. Then, by definition of matrix representation of linear operator T, okay, for each j is equal to 1 to up to n, T of alpha j, we can write T of alpha j is equal to summation k is equal to 1 to n a kj small a kj into alpha k. Give it as equation number 2 by the definition of matrix representation of linear operator. Linear operator. Okay. We know that how we can write the matrix representation of a linear operator. Okay. So any alpha j, T of alpha j is the linear combination of okay akj into alpha k. Okay. Since T of alpha j belongs to V, then from 1 replacing beta by T of alpha j, we get T of alpha j is nothing but summation k is equal to 1 to n inner product of T of alpha j alpha k into alpha k. Give it as equation number 2. Then from 1 replacing beta by alpha j here. We are replacing what? Beta by T of alpha j here. In the equation number 1, here beta we replace by T of alpha j. Then equation 3 comes. Okay. But the expression for T of alpha j as a linear combination of elements of the beta is unique. Okay. But the expression is T of alpha j. Every T of alpha j is the linear combination of elements from beta is unique because beta is the basis. Okay. Hence, we must have AKJ is nothing but T of alpha j and alpha k from equation number 2nd and 3rd. This AKJ is nothing but this scalar quantity. Which one is inner product of T of alpha j and alpha k. Why? Because the linear combination of elements of beta is unique. Because beta is the basis. Okay, hence we must have AKJ is equal to T of alpha j into alpha k. Okay, this is the proof of the theorem. Okay, now the next corollary is that let V be the finite dimensional inner product space and T be the linear operator on V such that for any orthonormal basis for the V, the matrix of T star is conjugate transpose of the matrix of T. Okay, the matrix of this T star is nothing but conjugate transpose of the matrix T. Let us say proof. Let V be the finite dimensional inner product space and T be the linear inner product space T. Let V be the finite dimensional vector inner product space and T be the linear operator on V. According to the previous theorem, then there exists a unique linear operator T star, okay, on V such that T of alpha beta, okay, inner product of T of alpha beta is equal to inner product of alpha into T star of beta. So all alpha beta belongs to V. Okay, by previous theorem we can write like this. Okay, let beta is equal to alpha 1, alpha 2 up to alpha n be the any orthonormal basis for V. Then we have A is equal to matrix AKJ with n cross n and B is equal to BKJ, where this is the n cross n matrix. Be the two matrices of linear operator T and T star. The matrix of T is A, the matrix of T star is B with respect to order basis beta. Okay, where T and T star are the two matrices. Now we have to prove that BKJ, this BKJ is nothing but conjugate of AKJ, conjugate of, okay, conjugate transpose. Okay, look at here. Conjugate transpose of matrix T. Okay, conjugate and transpose. We get here AKJ, but here AJK. It means the conjugate of A, transpose of A, and this bar is nothing but conjugate. Okay, conjugate transpose of AKJ is nothing but AJK bar. Okay, but we have by the previous theorem, AKJ is nothing but inner product of T of alpha J alpha K. Give it as equation number star, and BKJ is equal to T star of alpha J alpha K. Okay, consider BKJ is equal to inner product of T star alpha J alpha K. Okay, which is equal to by conjugate property of inner product space. This alpha k, inner product of alpha k and T star of alpha j bar, okay, which is equal to T of alpha j and alpha k bar. Alpha k is nothing but T of alpha k, okay, sorry, okay, this comes as a T of alpha k alpha j bar, okay, why from this one. T of alpha beta, T of alpha, inner product of T of alpha and beta is equal to alpha into T star of beta. Using this here, we can write inner product of alpha k and T star of alpha j, which is equal to T of alpha k and alpha j bar, which is nothing but bkj is equal to, but this is the nothing but ajk bar from star. Okay, ajk bar. This shows that the matrix of T star is the conjugate transpose of the matrix T. Okay. This shows that the matrix of T star is conjugate transpose of the matrix T. Okay. Now, the next point is adjoint operator. Let T be the linear operator on an inner product space V. We say that T has an adjoint. Okay, T has an adjoint T star if there exists a unique linear operator T star on V such that T inner product of T of alpha beta is equal to inner product of alpha T star of beta for all alpha beta belongs to V. Okay, this is the adjoint operator. Okay, the inner product of T of alpha and beta is equal to inner product of alpha T star of beta. Okay, now look at the theorem. Suppose S and T be the linear operator or the linear operator on an inner product space V and C is the scalar. If S and T possesses adjoints, the operator S plus T, C into T, composition of CS and T, okay, and T star will also possess the adjoints. Also, we have first one S plus T star bracket T star is equal to S star plus T star. Second, C into T bracket star is equal to C bar into T star. S into T, the composition of S and T star is equal to T star into S star. The T star of star is equal to itself T. Okay, we have to prove these four conditions. Okay, let proof. Let S and T are linear operator on an inner product space V. Suppose S and T possesses adjoint. There exists a linear operator S star and T star such that inner product of T of alpha and beta is equal to inner product of alpha and T star of beta. Okay, so let me give it as equation number 1. We have this condition equation 1, and inner product of S of alpha and beta is equal to inner product of alpha and S star of beta. Give it as equation number 2 for all alpha beta belongs to V. Okay, now to prove that S plus T possesses adjoint and S plus T star is equal to S star plus T star. Let alpha beta belongs to B be any vectors. Obviously, S plus T is also linear operator on V, since S and T are the linear operator. Consider this one. Inner product of S plus T alpha and beta is equal to S of alpha plus T of alpha and beta. Inner product of S of alpha plus T of alpha and beta, which is equal to linearity property of inner product space, which is equal to inner product of S of alpha and beta plus inner product of T of alpha and beta, which is equal to this nothing but inner product of alpha and S star of beta plus alpha and inner product of alpha and T star of beta from equation 1. Hence, by linearity property of inner product space, we can write like inner product of alpha and S star of beta plus T star of beta. Okay, by linearity property of IPS. Hence, inner product of S plus T of alpha and beta is equal to inner product of alpha and S star plus T star of beta. For all alpha beta belongs to V. Hence, S star plus T star is the linear operator. Okay. Thus, for the linear operator S plus T, there exists a linear operator S star plus T star on V such that inner product of S plus T of alpha and beta is equal to inner product of alpha and S star plus T star of beta. For all alpha beta belongs to V. Okay. Therefore, the linear operator S plus T possesses adjoint S star plus T star. Okay, but by the definition of adjoint, the adjoint of S plus T is S plus T bracket star, and hence by the uniqueness of the adjoint, we have S plus T bracket star is equal to S star plus T star. Okay, hence we have proved that S plus T star equal to S star plus T star. Second condition, we know that the scalar multiple of linear operator is again linear operator. Hence, C into T is a linear operator on V. Now, to prove that C into T possesses adjoint and C into T star is equal to C bar into T star. Okay, C bar into T star. For any alpha beta belongs to V, we have inner product of C into T of alpha and beta is equal to C into inner product of T of alpha into beta by linearity property of inner product space. Hence, which is equal to C into, but the value of this one is inner product of alpha and T star of beta, which is equal to alpha, inner product of alpha, and this C come into the inner product as a C bar into T star of beta. Okay. Hence, inner product of Ct of alpha and beta is equal to inner product of alpha and C bar T star of beta. This shows that for a linear operator Ct, there exists a linear operator C star T star C bar T star on V such that inner product of C T of alpha and beta is equal to inner product of alpha C bar T star of beta for all alpha beta belongs to V. For all alpha beta belongs to V. This shows that the linear operator Ct possesses the adjoint C bar T star. Okay, but by the definition of adjoint, the adjoint of Ct is C bar T star, and hence by the uniqueness of adjoint, we have C into T star is equal to C bar into T star. Okay, wait a minute. We know that the composition of two linear operator is again linear operator. Okay. To prove that S into T, S composition T possesses adjoint and S into T star is equal to T star into S star. Okay. For any alpha beta belongs to V, consider inner product of St of alpha and beta is equal to inner product of S of T of alpha and beta. Okay, which is equal to T of alpha into S star of beta by the definition from 1. Hence, is equal to inner product of alpha and T star of S star of beta. Okay, which is equal to inner product of alpha and T star S star of beta. Thus, for the linear operator St, there exists linear operator T star S star on V such that St bracket star is equal to T star and S star. Okay, so this shows that St possesses the adjoint operator T star S star. But by the definition of adjoint, the adjoint of St is given as St bracket star, and hence by the uniqueness of the adjoint we have St bracket star is equal to T star and S star. Okay, this is the proof of the third statement. Now we have to prove that the fourth statement. This one is to prove that T star possesses adjoint and T star of star is nothing but itself the operator T. For any alpha beta belongs to V, consider the inner product of T star of alpha with beta is equal to inner product of beta and T star of alpha bar by conjugate property of inner product space, which is equal to T of beta and alpha, inner product of T of alpha, beta and alpha bar. Hence, the T star of alpha and beta, inner product of T star alpha, alpha and beta is equal to inner product of alpha and T of beta. Thus, for a linear operator T star, there exists a linear operator T on V such that the inner product of T star of alpha and beta is equal to inner product of alpha and T of beta for all alpha beta belongs to V. This shows that T star possesses the adjoint T. Okay, this shows that the T star possesses the adjoint T. But by definition of adjoint, the adjoint of T star is given by T star of star. And the uniqueness of the adjoint T star of star is nothing but T. Okay. Okay. Hence, the operation of adjoint behaves like the operation of conjugation of complex number. This is the most important. The operation of adjoint behaves like the operation on conjugation of complex number. So today we discussed the adjoint operator and some theorems on adjoint operator. Which one is this one? Suppose S and T are the linear operator on an inner product space V, then C and scalar. If C and C is a scalar, if S and T possesses adjoint, the operator S plus T, C into T, S composition T, T star will also possesses adjoint. Okay, and the definition of adjoint operator is nothing but the T be the linear operator on an inner product space V. We say that the T has an adjoint T star if there exists a unique linear operator T star on V such that inner product of T of alpha and beta is equal to inner product of alpha and T star of beta for all alpha beta belongs to V. Okay, and this theorem one is also. Okay, so in the next chapter we will see the remaining part. Which one? The types of adjoint operators. Okay, sorry, the operators. Okay, what are the operators? Types of operators. Okay, thank you.